Hello guys. In this video actually we are going to see what is Reynolds transfer theorem. Okay. Now actually when we see this, we have conservation equation for mass. For mass, momentum, energy. That is all for control mass kind of system. Suppose to be more specific, let us say suppose we have this kind of mass. Okay. Now we have mass, momentum, energy equation for this mass. Basically, when we apply this conservation equation, it is assumed that our coordinate system moves along with the mass. That is for Lagrangian kind of system. However, in fluid mechanics heat transfer, this is a system generally we use control volume kind of system. So this equation is only applicable is only given. We know format is given for control mass kind of system, but now when we have to apply this kind of equation to a control volume, then what we have to do? So Reynolds transfer theorem is a link. This we'll see as short form RTT, is a link between control mass and control volume. System. Now, where in short derive the relation between these equations, control mass and control volume, and basically that is a Reynolds transfer theorem. Now, for simplicity, consider this as a initial quantity of a substance or a fluid. Okay. Now, after some at time t, this is at time t. Now, this whole mass in time delta t has moved to this new position. So this is a boundary at of this mass at t plus delta t. Okay. Now, suppose in this is a new system, mass at new time. Now, suppose if I name this as 1 and this part as 2. Okay, this is for simplicity. Now, at time t equal to 0, suppose this is the external property B. We are talking about anything, any property B. It can be mass, momentum, or energy. Now, B system, or we can say the system is like control mass at time t is same as B control volume at time t. This was initially our control volume, and the system or the fluid was at that place. So at time t equal to 0, our control mass coincided with the control volume. Now let us number this equation as 1. Now at time t equal to t plus delta t, now our control mass has moved a little bit. Okay. No, so B at control mass at t plus delta t is equal to, now at t plus delta remains the same. This is a boundary of control volume at t and T plus delta T. Okay, so this has remained same. So B control volume at T plus delta T. Now this is equal to this minus 1 plus 2, or we can say is equal to this as this, all this thing at T plus delta T, or we can say B control volume at T plus delta T plus B net out of CV of control volume. This term is net out of control volume, and this we put as 2. Now equation 2 minus 1 will get BCV at T plus delta T minus B control volume is equal to, sorry, this is control mass, this is control mass, BCV at T plus delta T minus BCV at T, okay, plus B net out of CV. Okay, now dividing equation 3 by time delta T, what we'll get is, this looks similar like a derivative, f of x plus h minus f of x by f h. So that is dB control mass by dt is equal to dB control volume by dt plus B dot. Time derivative actually we are, for simplicity we are denoting as B dot of control volume out. Okay, so this is Reynolds transport theorem.